Hello, I'd like to introduce you to a new tool called the ModelInspector, which is a tool for inspecting probability models stored inside of RooFit workspaces that have been organized in a way for the standard RooStats classes. So in particular, the workspace needs to have both a probability model and a model config object that gives some additional information. So I'm going to start off with making my model with the hist factory tool. So this is just a very simple XML file that is going to combine two input files. So there we go. I have a configuration file with channel 1 and channel 2, which I'll show you in a second. And I'm going to make one measurement that's going to be end up being stored. So the output prefix is my results area. Example is the prefix, and then it will be underscore channel 1 and channel 2 for the individual models and underscore combined for the combined model. Then my measurement is called the Gaussian example, and then my parameter of interest is the signal cross-section over the standard model. And before I was setting these constants to be these parameters to be constant, but I'm just going to turn that off real quick. Okay, so all of my parameters will be floating. Now let me open up real quick the example channel.xml file. So it's made out of, let me make this a little wider. It has three samples. There's a signal sample, a background 1, and a background 2. And the signal as a systematic 1 affects it, and it also has a parameter, our parameter of interest, which is how much signal there is. Then there's the background 1 has systematic 2, which affects it, and background 3 has systematic 3, which affects it. And then if I open up example channel 2, it's just a copy of the same thing, and you see but now systematics 4 and systematics 5 affect the backgrounds in the second channel. Okay, so I'm going to quick run hist to workspace on my example XML file. So let me look in my results area. Okay, I have made a new results file. So now let's try using the ModelInspector, which is the point of this. So in my area here, I have a new macro called ModelInspector. So I'm going to type root, and then I'm going to load that macro with a plus sign because I need a click to compile some libraries and things for it to work. Okay, so there we go. Now I can type ModelInspector, and as most of these macros all take the same input, it's just 4 strings. So the first is the name of the file, the second is the name of the workspace stored inside, the third is the model config name, and the fourth is the dataset name. And normally you would look inside of your file and see what all of these things are called. Since this was made with hist to workspace, these things have a kind of standard naming. So really what I need to do is point it to the file that I just created. So that's in results example, and I can just tab a little bit here, and I see, there we go, combined Gauss example model.root. That's what I want. So combined Gauss example model.root. And then the other things will have their default arguments. Okay, so there we go. So now I'm running the ModelInspector, and at first these plots are just based on whatever the values of the parameters in the workspace are at first. And you see I have a slider for each one of the parameter of interest and all of the nuisance parameters in my model. Since this, and then I have the data points, and since the data points don't really seem to have anything to do with where my model is right now, I have a fit button here, so I'll click fit, and abracadabra, the model has now been fit. If you look back in the root window here, you see it fit and what the values of the best fit are. And so, for instance, the luminosity best fit was 1.004, and when I look here, 1.0045, and when I look at the slider, that's the value that it's using. Similarly, the parameter of interest was 1.089, and I see 1.09. Okay, great. So so that's the best fit model, and the yellow band around it here is the error from propagating the uncertainty of the fit through the model. And then the red and the green are things that I can play with. And basically the red curve corresponds to if each of the parameters had a value equal to where the high end of the slider is. So for instance, the luminosity, if I just grab that and make it be bigger, I expect a lot more events than I see, and I can bring it back down to something more reasonable. And similarly, if I grab the low end of that slider and make it small, I can expect 0 events. Okay, so, and then the middle adjust the sort of nominal model, which I can move around. Okay, so let me fit it again, put it back into some reasonable case. So these red and green overshoot the actual error of the model because every parameter is being pushed up by 1 sigma, which is sort of overkill. But it is nice that you can go in here and play. So we know that systematic 1, for instance, modifies the first channel, so I can move it around and see what would happen. And then systematic 2 it basically just moves around that first bin, it looks like. Then systematic 3, what does it do? Okay, that moves around that second bin. And systematic 4 moves around the first bin and the second channel. Systematic 5 moves around the second bin and the second channel. And the signal cross-section, which is the thing I'm ultimately interested in, look at this. Right now, it thinks that this parameter should be 1, but if I move it all the way down to 0, I see there's no signal at all. And that signal is correlated across both channels. So as I move it around, I see how it affects the model. So this is a nice way to kind of see what's going on, and when you're done, you can just hit exit. Okay, thank you very much.